Yeah, so as you all know, there is this new topic today, and we are going to learn about bit manipulation. Okay, quite an interesting topic actually. So I had asked you guys to study basics of bits and also study basics of bitwise operators. Can you name me those operators, basic bit operators? So we will be looking at all of those, and then we will try to understand that why they are important. Okay, and once we apply it to the questions, then you will be even more clear. Okay, what is a bit? First thing, what is this bit? So if let's say I have a number, okay, which is in base 10 notation. So this 5 is in base 10 notation. Now if I have to convert it in base 2, all of us know how to convert a number in base x, right? So if I convert it into base 2, then the equivalent of this will be this in base 2. So these things are called as bits. All these things are called as bits. Another example, if 3, which is in base 10 notation, it will have base 2 notation like this. Now base 2 notation is also called as binary representation. So these representations are nothing but binary representations, and in any binary representation each digit is being referred to as a bit, right? Now few things that I will consistently be using from now onwards in every class, some notations that I want you guys to get extremely comfortable with are, there are many bits. So let's say there is a binary number like this. Okay, so which is the most significant bit? By most significant bit I mean, is this first one the most significant bit or this second one the most significant bit? Which one? Yeah, second one is the most significant bit. Why? What is the significance of the bit? What is the significance of a bit? Significance of a bit is the value associated with it. So if a bit is at ith position, then how much is the value associated with it? 2 raised to power I, right? So if the value of I increases from here to here, then the value of 2 raised to power I will also increase. What does it represent? It represents 1 into 2 raised to power 0. It represents 0 into 2 raised to power 1. And what does this represent? 1 into 2 raised to power how much? 2, 3, 4, 5, 6. Right? So this is the most significant bit, and this is the least significant bit. Okay? So whenever you are solving a question based on bits, where you play around with the bits, then you actually journey across the bits, and that journey can either be from here to here, which is most significant to least significant, or it could be the otherwise. Most of the times it is like this. So one more thing, to number the bits, I would number them like this in any question. So I will call it bit 0, bit 1, bit 2, bit 3, bit 4. This is how I'll number them. So higher the number, more significant the bit. Lesser the number, less significant the bit. Okay. So these are few things that we will be taking care of. Okay. Now few more things to understand over here is that as you said, there are few very important and basic bit operators. The easiest of them are and or, right? All of you already know about this AND operator and this OR operator. Are these bitwise operators? My first question. Are these bitwise operators? No, these are not bitwise operators. Which kind of operators they are? They are logical operators. Very good. Logical operators. So logical operators need logical operands. Operand 1, operand 2, both of them should be logical. What do I mean by that? That this thing can be a statement, okay, and this should evaluate to either true or false. Similarly, this should evaluate to either true or false. Same is the case over here, that the operands should have an ultimate value of either true or false, right? In case of logical and logical OR, right? But in bitwise AND, that bitwise AND is just like this, single ampersand, and bitwise OR is single pipe. Okay, So this is the bitwise and this is the bitwise OR, and what will be their operands? Can you think of their operands? Their operands will be nothing but bits. Okay, bits. Yeah. So this value will be a bit which can either be 1 or 0, and this value will also be a bit which can either be 1 or 0. Okay. So that is the key difference between them. Another thing, bitwise operators in general are very fast. They are very fast. So if let's say you are doing some arithmetic operation, let's say multiplication, okay, let's say you are doing multiplication, and if let's say you are trying to achieve the same thing that a multiplication does by using bitwise operators, then the second thing will be more fast. Why? Because the closest form of code that a computer can understand is a binary code. All of you would have seen that when you compile your code, then there is a binary file that gets created, yes or no, right? Are you aware of .out file? C++ guys, when you do that, that gets created, right? That is a binary file. So what does that contain? That contains just a combination of 01010101, which is the equivalent form of your code that you wrote, right? So that being the reason, important thing to understand is that computer understands bits very closely. So the bitwise operators are executed in a faster mode. Okay, cool. Now all of you understand what is the meaning of and what is the meaning of OR. So if let's say this bit is also 1 and this is also 1, then only the value of and will be 1, otherwise it will be 0. So even if one of them is 0, then the bitwise AND of 2 bits is going to be 0. Okay. Similarly, bitwise OR. Okay, bitwise OR. So what about bitwise OR? When will bitwise OR be evaluating to 1? So if either of them is 1, then the value will be 1. So what does that mean? For bitwise OR to be 0, what should happen? Both the bits should be 0. Otherwise, it will be 1. Even if one of the bits is 1, it will be equal to 1. Right? Okay, cool. So we are done with the bitwise and we are done with bitwise OR. Now let's move ahead from here. Now two very important, in fact the most important that we'll be using operators, those are left shift and right shift. So let us understand, these are very easy things. So first of all, this is denoted by this sign. Have you seen this sign before? Where is it used? Cout, right? Yes, this is used in cout. Those of you who use C++, when you cout something, you use it, right? So this is an overloaded operator actually. Sometimes it means output when used with cout, and when it is used as a binary operator, that is when it has 2 operands associated with it, then it is thought of as something different, which is a left shift operator. Okay, so this symbol denotes this also and this symbol denotes this also, which is nothing but left shift operation. I'll tell you what is left shift operation exactly. Similarly, right shift is denoted by this. Have you seen this also? Where have you seen this? Yeah, you have used it with seen. So similarly, this operator is also overloaded operator. So these two bitwise operators are overloaded operators, and your compiler intelligently decides that what did you mean while you have written a code. I mean, which version of them you wanted to actually use by semantically understanding your code. Okay, cool. So this was basics of just how to denote left shift and right shift. Now we will understand what do they exactly mean. So simple, whatever is the name, that is the job. Okay, so if let's say there is a binary number like this, okay, now left shift by 1 unit, if let's say you are performing left shift by 1 unit, what does that mean? So just think of it in this way, that there are many bit positions. Okay, what will be the initial bits? What will be the initial bits, if at all, for this number? If this number's highest most significant bit is 1, all of them will be 0, right? So I can just prepend all of them to 0. Okay. So left shift by 1 unit means that you will shift all the bits by 1 unit to their left. Once you do that, what is going to happen is this remains 0, this remains 0. Now 1 comes over here and then 0, 1, 0, 0. And then once this is vacant, then this remains 0. So this is the meaning of left shift. Every bit shifts 1 unit to its left and the position that remains vacant, that turns to be 0. Okay, this is what left shift is. Okay, now tell me what impact will it have on a number? If you left shift a number by 1 unit, will the resultant number be greater or same or smaller? What will it be? It will definitely be greater. And how greater it will be? So if you try to understand that, let's say I have this. Okay, so this one, let's say it was present at ith bit. Everyone listen to me very carefully. If this one was present at ith bit, then the contribution of this one in the total value of the number was 1 into 2 raised to power I. Yes or no? Correct? It was 1 into 2 raised to power I. Now once it has got shifted by 1 unit towards here, can you tell me the new contribution? It should be 1 into 2 raised to power how much? I plus 1. Correct? Yeah, because it has been shifted from ith place to I plus 1th place. Okay? So if you, let's say, try to write down this thing, you will write 1 into 2 raised to power how much? 0, 1, 2, 3, 4. 4 plus 0 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 and plus 0 into 2 raised to power 0. Now once the left shift has been performed, then what will happen? The power of all of these will get incremented by 1 unit, isn't it? Right? It's very simple to understand. This one which was here, this is now shifted here. This one which was here is now shifted here. If let's say there was a 1 over here, then this would have got shifted over here. Okay, so now, and whatever is going to come here as a vacancy thing, that is going to be nothing but 0. Okay, so this was the initial value, and the final value that I am going to get, in that it will look like 1 into 2 raised to power 5 plus 0 into 2 raised to power 4 plus 1 into 2 cubed plus 0 into 2 squared plus 0 into 2 raised to power 1, and plus that will be 0. So this is nothing but 2 times of this. So what does a left shift of 1 unit mean? Left shift of 1 unit is similar as multiplication by 2. So if you have to multiply a number by 2, if you have written a code where you are doing x into equals to 2, you can do x equals to x left shifted by 1 unit. So this left shift operator takes 2 things. First thing is that thing which you want to left shift, and second thing is the number of steps by which you want to left shift that thing. Okay, so these are the 2 intakes of this left shift operator. Another thing that I want to ask you guys is, so left shift operator is clear to all. Now tell me one thing. If let's say you have written this thing, okay, so everything here is an operator. This is also an operator, assignment operator, and this is also an operator. So which operator executes first? The operator with the high priority or lower priority? Which one? The operators definitely with higher priority will execute first, right? Now can you tell me what kind of priority do bit operators have? So please explore it in your language, and let me tell you, bit operators have a very low priority. Their priority is lower than logical operators. So you should try to be very, very safe. I mean, writing such kind of expression might run you in risk. Why? Because it might so happen that first this gets executed and then this gets executed, but that is not what you want. So you have to use the brackets. Okay. So let's say if you are trying to compare something with, you are trying to compare whether P is equal to Q left shifted by 1 unit. Okay. So what is your intention here? Everyone see here, everyone look. What is your intention? This thing is nothing but 2 into Q, right? So if let's say you had written P equals to 2 into Q in your if, Nothing would have gone wrong. Why? Because which one has a higher precedence? Does multiplication have a higher precedence, or does logical equal to have higher precedence? Can you tell me that quickly? Multiplication has a higher precedence, but in this case, this has a higher precedence. So that being said, you have to put this thing in bracket. So you have to play very carefully while you are playing around with bit operators. It will make your code faster than before, but these kind of things you have to take care of. So the rule of thumb that I want all of you to remember is very simple rule, and that rule is whenever you are playing around with bitwise operators, please put them in braces if you are not sure of the precedence rule. Okay, I hope you will not make such mistake. Okay, people make such mistake and then they keep wondering what went wrong. Okay, because it is hard to debug. Another question that I have from you is, yeah, shifting left by 1 unit is like multiplying by 2. Okay, what does something like this mean? So if I do q left shifted by 5 units, what does this mean? What will be the final value of 2? So it will be nothing but q into 2 raised to power how much? 5. So if you left shift something, if you left shift a number num by I units, then this is going to become num into 2 times of I, because one left shift is one multiplication, so I left shift should be I multiplications by 2. Okay, another thing, again, to be very careful, I am telling you again, I will not tell these later, okay, because I see people make mistakes, that is the only reason. However, I will not want to repeat these small things. So while you are doing this thing, you have to be extremely careful about one thing. Apart from the precedence, there is one more thing that you have to be careful about. Will somebody tell me that? Yes, very good. Overflows can happen. Overflows can very much happen. And now, if let's say the data type of this is int, then this thing would also be assumed by your compiler to be an int. Okay, by your system to be an int. And if it assumes that, then it will simply overflow. Did you get my point? So what will you do that? For that, you can typecast it into long or long, whatever you feel is the necessary thing to do. So I have seen people doing this blindly without caring about the data type of the result of the expression. Is this clear to everyone? Yes, no? If you want, you can make notes of these errors. It will help you debug if you make errors later. Okay, cool. So this was another thing to be kept in mind. Okay, so all of us now understand the physical significance of left shift. Left shifting by I unit means multiplying by 2 raised to power I, and this is much faster than manually multiplying by 2 raised to power I. Okay, tell me one thing, what will be the value of this expression, 1 left shifted by, let's say, 3 units? Can you write the binary form of this expression? When I left shift 1 by 3 units, what binary form am I going to get? Again, this is a very powerful operator in the term that if you want to generate a power of 2, if you want to generate a power of 2, then you just have to do I1 left shifted by I units. What is it going to generate? If you shift 1 by I units to the left, it is simply going to generate 2 raised to power I. And sometimes generating something like this is very important. So all of these I will be using, that is the only reason I am saying. So be careful, don't miss anything. Okay. So and also the binary equivalent of this will be something like this. There will be just one bit which will have 1 and everything else will be 0. Right side also and left side obviously. So this kind of thing is also called as a bit mask. Let me tell you that. Such kind of thing where just one particular bit is on and everything else is off. This thing is also called as a bit mask, and let me tell you, this is the heart of bit manipulation. This is the most important crux behind bit manipulation. This will be constantly used. Okay, so if you have to generate a bit mask where the bit is on at ith position, you simply have to generate this and nothing else, taking care of the precedence thing and overflow thing. Yeah, so this was about my left shift operator. Now come to right shift operator. So what according to you should right shift operator do? What should be the equivalence of right shift operator? Cout, right? Yes, this is used in cout. Those of you who use C++, when you cout something, you use it, right? So this is an overloaded operator actually. Sometimes it means output when used with cout, and when it is used as a binary operator, that is when it has two operands associated with it, then it is thought of as something different, which is a left shift operator. Okay, so this symbol denotes this also, and this symbol denotes this also, which is nothing but left shift operation. I'll tell you what is left shift operation exactly. Similarly, right shift is denoted by this. Have you seen this also? Where have you seen this? Division by 2, right? Because what right shift essentially does is nothing but, if let's say you're trying to perform a right shift of this by 1 unit, then it is just like shifting every bit 1 unit right. So this bit will get dropped off, okay, and then there will be a 0 here, then this 1 will come here, this 0 will come here, and this 1 will come here. So every bit loses its significance from 2 raised to power I to 2 raised to power I minus 1. And since this is being done, the resultant will be something which is division by 2. Okay. So if let's say you are dividing a number x equals to x by 2, then you can write it something like x equals to x right shifted by 1 unit. These both are same and this is faster. Okay, do not worry about cases where you can have a 1 over here. So when you right shift it by 1 unit and let's say the last bit was 1, then there is a value that you are letting go of. But should you worry about that? Do you think that the result will not be division by 0? What are your opinions? Can you just type that? What is the value of this? 1 plus 4 is 5 and 5 plus 16 is 21. And what is the value of this? 2 plus 8 is 10 and 10 is equal to 21 upon 2. So why that will not happen? Because this division that I wrote over here, which kind of division is this? This is integer division, okay? And integer division by 2 will not have a different result whether you consider x, whether you consider x plus 1. Yeah, if x is odd. So these are few things to be kept in mind. Now, one more thing, this is just for your, because some of you would not have written a lot of code on bit operators. So instead of writing something like this, you also write something like this, yes or no? Which kind of operator this is? This is a shorthand operator, okay? So there is shorthand operator for left shift and right shift also. So if let's say you want to left shift by 5 units, one way to do is this, and shorthand operator says something like this. And same thing applies for right shift operator also. Now let me ask you one simple question. You are given a number x and you have to check if this x is odd. You have to check if x is odd. What will you do? So see, one classical way to do is that check the remainder. So if the remainder is not 0, that means it is odd. So I think everybody is well versed with this, correct? But now let me ask you one very simple thing over here. Can you do it without using these operators? Can you just use bitwise operators and do it? Can you do that? So the answer is yes, you can actually do, and some of you are answering it. So tell me one thing, if a number is odd, then its binary representation, what will be present at B0? What will be present at B0? 1. It will be 1 for sure. Can I say that? Yes. Why will it be 1 for sure? Because let us prove it by contradiction. Okay. If let's say this was not 1, if let's say this was 0, then no matter which bits were on, everything is nothing but a power of 2. Yes or no? Everything is denoting nothing but a power of 2, and if power of 2 will always be even, and if you sum up even numbers, the result will be what? If you sum up even numbers, the result will be an even only. So the last bit has to be 1, so that this 1 gets added to even, and even plus odd becomes odd. So the last bit will be 1 for sure in case of any odd number, right? Very good. So one thing that we all understood is that in odd number, last bit will always be 1. And how about even number? What will be the last bit in an even number? It will always be 0. Okay, because the moment you have 1 over here, then odd plus even will be odd, it will not be even, right? So again, very simple thing, but important to understand. So now you tell me one thing, how do you check whether the last bit is 1 or 0? So if you take a look, this thing is exactly doing that, yes or no? This thing here is exactly doing that. The last bit is x mod 2, yes or no? Yes, no. How do you convert a number into its decimal equivalent? First you take mod, then divide, then again take mod, then divide, right? So this is exactly doing that. But what is another way of doing that? So some of you used bitwise AND operations and then tried to do it. So let me ask you one simple question. Let us take about bitwise AND. So can somebody tell me the result of 5 and 7? What will be the bitwise AND of 5 and 7? 5 is 101. This is 111. What will be the result? Okay, so how do bitwise ANDs operate? Bit attacks bit. Bit attacks bit. Bit attacks bit. So bit 0 is ANDed with bit 0 of this. Bit 1, sorry, this was bit 0. Bit 0 is ANDed with bit 0 of this. Bit 1 is ANDed with bit 1 of this. And bit 2 is ANDed with bit 2 of this. So 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1. So the result of this is this. So this is how bitwise operators are applied, one by one at bits. Okay, even if let's say there were many numbers, let's say there was a number with representation as this, and then a number like this, and then let's say a number like this, then again this, and this. Okay, this, and this. Similarly this, and this. So while you are taking AND, even if one bit is 0, even if one bit at that particular position is 0 in any number, what will be the resultant bit in the number at that position? It will be 0, right? So all the bits have to be 1 for the resultant to have 1 at that particular bit position. Correct? This is a really important thing to be kept in mind. Okay, so let's come back to this. Here you have to check whether the last bit has 1 or not. So think of a number which just has 1 at its B0 and everything else is 0. Can you tell me what number is that? 1, right? So if you take AND of a number x with 1, AND of a number x with 1, and let's say the result of this thing comes out to be 1. If the result of this thing comes out to be 1, what does it mean? It means that the last bit of this x was 1, right? Because x in its binary representation might have been something like 0, 1, 1, 0, 0, 0, and then let's say the last bit was 1. And this thing is clearly just here 1 and everything else 0. So these all and these all get evaporated. Why? Because all of these are 0. Only this and this will collide and produce some non-zero result. Now if this is 1, then the result of this AND will be 1, and if this was 0, then the result of this AND would have been 0. So if the value of x and 1 is 1, that means the number is odd, otherwise it should be even. So instead of making this check, you can just have if x and 1, okay. Now if this thing returns 1, 1 is regarded as true. So if this thing is true, that means the number is odd, and if not of this, while you use not, please protect it within braces, then it is even.